So hi everyone. Thank you so much for having me here and also for being here. I'm Sharuth. I'm in my 4th year. I'm a PhD student at MIT. I work with Professor Philip Isola and Professor Stephanie Egelka. These are my wonderful 2 advisors. And today I'll be talking about one of our recent works, which is called Unpaired Multimodal Representation Learning. In collaboration with some of my friends and again my advisors, we are going to be presenting this work at ICLEAR 2026 in Brazil in the next few months. For the presentation, I've tried to keep it more at a high level and focusing more on the results and the intuition. But I'll be touching briefly on like some technical details about theory. But yeah, feel free to ask me questions ranging from like anything in the whole slide. So yeah, let's get started. Okay. So whenever we are training on a particular modality, for instance, if we have a bunch of images and we want a model that can use those images and predict well on a new image that we haven't seen. So what we'll typically do is take that bunch of image data or collect more image data and train a model on top. And the model might be a vision transformer or something else, which just handles and knows how to take as input a bunch of images. Similarly, if you have like a bunch of text data, what you would want to do with that is instead train a text model on top. For instance, our well-known large language models like ChatGPT, Gemini, and so on. So the conventional wisdom says that to get a better model, you just need more data of that modality. For instance, if you need a better text model, you need more text. And if you need a better vision model or a better image model, you need more images. But there has been some research which actually suggests otherwise. So in the left here, I'm plotting the accuracy of a trained model. And on the x-axis is how much paired image text data that I used to train that model. And the y-axis accuracy corresponds to an image task or a vision task. So as you see here, as we increase the amount of paired image text supervision, you see an improvement in the vision performance. So if you get more and more text, which is paired for your image data, you actually can improve on your image tasks. So it's not like true that if you have to improve on your image tasks, you just need image data. You can actually improve with text data as well. And this has been the basis of a lot of multimodal representation learning papers. Some of the models which are trained on multimodal data are like CLIP, GPT-4V, Flamingo, and so on. So the idea is that they take a bunch of paired data, images paired with a bunch of text, and then they train a model on top of it, which learns to extract features and information from image and text jointly. And most of the works and the models in this whole space have been solely based on paired data. So the question that we are trying to ask here is, but do we actually need paired data? And why is this question actually important? So here is one particular example. So Lion is the largest open source paired data repository that is known so far, developed by some of the amazing researchers in UW, Stanford, and so on. So the size of this repository is just like 5.85 billion compared to the amount of unpaired data on the internet. For instance, even Google Photos has a data as of November 2020, 4 trillion, and there's like 28 billion new uploads per week. Similarly, Common Crawl, another data set of web pages collection, has about 250 billion estimate of the amount of data present. So there's definitely humongous amount of unpaired data on the internet, which we are not able to leverage directly because we don't have paired data corresponding to it. So if there's a way we can actually extract a lot of information from unpaired data, that would actually be really helpful. So that's the key question that we are trying to address in this particular question, which is, can unpaired data from another modality, say I want to train my image model, but I want to test if unpaired text data can actually be useful to improve my image model. And what would be the ratio? For instance, if I want to improve my performance by 1 point, do I need X amount of image data versus how much, versus Y amount of text data? What is the ratio between X's and Y's? Is it possible that to actually improve an image, you might just need 1 extra additional text, but like 10 different images? That is, you can have a model which learns better from another modality, even when your target task is vision. So these are some of the questions that we'll be answering in this particular presentation. So some of you might be thinking that how would unpaired data actually be useful in this case? If I have a task which is based on images, what kind of unpaired text data would actually be helpful? And if we don't know any pairings, how can we extract the information? So this particular slide gives an intuition about that. For butterfly fanatics out here, they might already know some of the things that I'm talking about. But say that your task is image classification, and your data set is a bunch of images of butterflies. So what you do is that you train an image model on top of this data set. You take the representation of this model and test it on your downstream task. So for this particular image of a butterfly, this model actually predicts it. This is like the output probability of the model. So the model is predicting its breed as like viceroy butterfly and not monarch. But monarch is coming pretty close second in this probability distribution. Now assume that you have a bunch of unpaired text talking about animals, birds, plants, butterflies, and so on. But somewhere in the text, there are these few phrases. So let's just particularly focus at the last one, which says that viceroy butterfly actually resembles a monarch butterfly, but also has a line across the hind wing. And any model that actually can understand this particular text would know that a viceroy butterfly has a line across the hind wing. And if I make sure that somehow this language model or a model that actually understands this text shares some information with the image model, then we know that the prediction for that particular image should actually be monarch and not viceroy. So that is the whole idea. Even though this particular text prompt, it's not paired with this given image, but because at the whole distribution level, there are some features which the image, which might be useful for the image model. If we somehow enforce the text information to be consistent with the image information by making some sort of consistency loss between the image model and the text model, then we can actually improve the predictor of a image-only model by just using this extra text data. So in this case, the model now predicts it as a monarch butterfly and not viceroy, which is the correct prediction. So this is a very simple example and an intuitive example of how can unpaired data from another modality, which is text in this case, be useful to improve vision models, that is image. So we also develop a bunch of theoretical guarantees for what we are trying to say here. And I'll just like touch upon this, but the whole idea is whatever data we collect, which is images and text, they represent some underlying distribution of the world. The way we collect this data is through sensors, for example, cameras or descriptions of different scenes and so on. But most of this information represents the earth that we live on or the reality that we are in touch with. So as long as there are some shared features across these two modalities, which is image and text, we should be able to extract them, even if it's unpaired, and represent the reality better. So that is like the mathematical model of what we are dealing with here. Say you represent your ground truth reality as this latent variable z star that we don't know about. But we are collecting information about this z star in two different forms. Say modality X is images and modality Y is text. And each of them is some data processing function of the ground truth world. So to simplify things, let's just assume that this data processing function is linear. That is, the way you collect any data in modality X, it is a linear function of your ground truth world. We can say theta c is the ground truth world, along with some modality specific information, which we denote as theta x. Similarly, for distribution y, we have a linear combination of the ground truth world theta c and some modality specific information, which is denoted by theta y. So the idea is each of the images and the text will be representing some information over the world, but also might have some features which are specific to how you represent that modality. For instance, if I am writing a description of a scene versus someone else is writing a description of a scene, I might have some stylistic features or the way I write, which might be very specific to that modality and might not be even visible in the vision domain. So this particular formulation actually handles both the things. That is, both the modalities share some centric information, which is theta c about the world, but also have some modality specific information. Now, under this particular data generating process and this model of the world, you can come up with very simple conditions under which even unpaired data from another modality can actually improve your model. And this is one of the results. So as long as BCJ, which is the coefficient in the second modality of the ground truth world, which is shared across both the modalities, that is theta c, as long as this coefficient is full rank, that is this matrix that you get is full rank, then you can say with guarantees that if you use the data from both the modalities together, you will have a strict improvement in the information of your estimator, or you'll have a strict reduction in the variance of your estimator, and you can estimate the ground truth world better. So this is like this touching upon some theoretical results. There are more in the paper. Yeah, but I'll just skip this in the interest of time as well. But yeah, so basically you can come up with guarantees under which your data from another modality should be helpful. Now we want to take all these theoretical insights and convert them into a very simple algorithm without forcing any sort of extensive inductive biases. We just want the model to automatically figure out when is the data useful, and if it is useful, it just extracts useful information from it. And that is the idea of the algorithm here. It's extremely simple. So say you have this image on the left, butterfly, and you have some unpaired text data. I'm picking up one sample from that text data, which talks about an eagle. So what I do is I convert the images and the text into a bunch of tokens, which is denoted by these yellow boxes, which are the input tokens to the model. Then, because each of the modality has some modality-specific components, I pass each of these pixels or like each of these tokens through some modality-specific encoders, which are denoted by fx and fy in this case. So they are just processing this information, which might lie in different dimensions, and getting it together in some joint space. Now, all I do is I force both the embeddings to pass through the same network H. So H is another neural network, but what you might be observing here is whether the input is an image or whether the input is a text, both of them go through the same network H. So the idea is that if there is some shared information between X and Y, H should be able to extract that and encode that. And as long as H does that, you can also have modality-specific decoders which take that information from X, which is this joint information, and convert it back into the tokens. So now, to train this particular model, you can have like a lot of variants. The particular variant that we use in the paper is next token prediction or next patch prediction. For instance, for this input 1, 2, 3, the goal of the left model is to predict the next tokens, which is denoted by like 2, 3, 4. And similarly, on the right side, for 1 prime, 2 prime, and 3 prime, the goal of the network is to predict 2 prime, 3 prime, and 4 prime, which is the classic next token prediction loss in like language models. So this whole architecture and this whole method, which we call UML, or Unpaired Multimodal Learner, is inspired by Ilya Sutskever's talk at Simons Institute. The talk is called, and the link is attached on the left, it's called An Observation on Generalization. Highly recommended talk, really, really cool stuff. So the idea is very simple, that if you have a very good compressor, say you have like a very good compressor C, and if you have two different data sets, X and Y, you don't know how much information is shared between X and Y. But if you give the compressor this X and Y data together, so it should be able to compress the data jointly with at max length of what it would have taken if it were to compress X separately and Y separately. That is, if you take X and Y together and pass it through the compressor, it should have the upper bound of this compressor in terms of the number of lines it needs to represent that data by, should be upper bounded by if it were to represent X separately and Y separately. And the difference of the left term and the right term is what is known as algorithmic mutual information, which is when X and Y actually share data. So a compressor should be able to exploit that information and use fewer lines of code to actually represent that data. And this is an exact generalization of this argument. So you don't worry about how much information is shared. You just have a bunch of data, you pass it through the model, and you make sure that there are some layers of the model which are shared across the different data sets. So you don't treat different modalities as different data. All the data is, like data collected from different modalities is just data, and it's just representing the world that we live in. So you shouldn't treat them very differently. At the end of the day, they should be processed through similar networks, and if they're processed through the same network, the model might have the capacity to actually extract meaningful information and meaningful signals from the two modalities. This is the whole algorithm, very, very simple idea. And now I'll be coming on to the experimental results about how this works. So the first we'll be observing how data from another modality can be useful or on your primary modality of interest in terms of some empirical performance on some benchmarks. So here again, the benchmarks that I look at, this is one of the examples. So on the left, we have paired data, where corresponding to every image, we have a textual prompt which describes the image. And on the right, we have unpaired data, where although there might be shared correlations amongst the two data sets, that is the image data set and the text data set, but you have no idea about which text corresponds to which image. So you have like fully unpaired data with no correspondences known. So in this case, these are some of the data sets, and they range between healthcare, animal detection, sarcasm detection, and so on. So the first row in this table corresponds to the unimodal baseline, which just means that I take images from all these data sets, and from each of the data set individually, and I just train a model on top for whatever downstream task of interest that I have. For instance, for mustard, it's sarcasm detection. Mimic is a healthcare data set, so the classification problem is breast cancer detection, and so on. So for each of the tasks, you can see that on the top row, we have the unimodal performance, and on the bottom row is just taking unpaired data without any correspondence is known, and with the architecture that I just showed in the previous slide. And you can see that you can get significant boost on top of it without any additional parameters and without doing anything fancy and without any specific inductive biases. All you have to do is pass the data together through the same model, and that's it. That does the job. And it has significant improvements on a bunch of these benchmarks. Also, this method is trained fully self-supervised. We are not using any labels anywhere. The supervision comes from the data itself and the fact that you are passing different modalities through the same network. You can also exploit the same thing if you have more labels present, that is, if you have more supervision. So assume now that you have unpaired data, but you also have some labels present with that. For instance, on the left, I have images, but I know that the images belongs to which class or which label. In this case, red panda, dog, and so on. And on the right, I have a bunch of text, and again, I know which label the text describes. So in this case, I have strictly more information than what was in the previous slide, right? Because there is some level of correspondences even at the label level in this case. So here UML has this special variant, which is a simple generalization of what we saw before. So instead of predicting the next token or the next patch, you can predict the label directly. For instance, you process the image and the text the same as before in a bunch of tokens. You average out the embedding of a token to get Z and Z prime. You pass it through modality-specific encoders. Finally, you pass it through a shared network H. And the task of the way the whole network is trained is to predict the label of that particular text or of that particular image. And in this case as well, these are different settings in which we tested our work in terms of which are the layers that we actually trained the model. And on a bunch of benchmarks, which are standard vision tasks when it comes to checking multimodal performance, we can see decent improvements in performance across a range of them. In few-shot learning, you can see even more performance gains. And when I say few-shot learning, I just mean that the amount of training data set is actually reduced. So for each class, you only have a few data points. So in limited data setting, if you have data from another modality, even when unpaired, it can lead to quite a lot of improvements. The last column here also shows the average improvement across all these benchmarks. Not just image and text, you can do the same for audio, which is shown here. So these are another two data sets where we have image, text, and audio together. So here we can see that if you use audio plus image unpaired or audio plus text unpaired, you can improve over just the audio only baseline just by passing all the data together through shared networks. Yes, so not only co-training, there are different ways you can test that how data from another modality is useful. And this is the second way. So assume that you have a network that you train on text modality. So the weights of this network are initialized by the information that is present in text. And now you take this network and train it and fine-tune this network on your image task. So the idea is that if text and image actually share important information and there are correlations that a model can exploit, initializing from another modality might be a good starting point to train on your target task. So you initialize the model with text embeddings or a model trained on text, and then you fine-tune that model on image tasks. And you can see here that in two different settings that we actually tried it on, and the test task is ImageNet in this case. If you initialize the model from a language model, which is BERT, then you can have much more performance than if you just train the model from scratch, which means that language models have biases which are useful when you train vision models, even when there's no paired information available. So this is another example. Finally, what are the implications and the analysis of the learned representations when we actually use data together and train them using UML? Yes, so in this particular slide, we observe existence of what we call multimodal neurons. So when I say multimodal neurons, I just mean that the model never sees any paired data, but eventually, after training, there are some neurons in the model which spike when the same content across different modalities is shown to them. For instance, if I'm showing sarcasm as an image versus if I write a sarcastic text, the same neuron actually spikes and fires up. And you can test that out. And that's what we are showing in the plot here on the left, which shows this cross-modal correlation. That is, how many neurons are there which fire up when the same semantic content is shown in different modalities. So the task here was sarcasm detection, and you can see here whether the samples are sarcastic or non-sarcastic. Overall, as the training evolves, you see the emergence of multimodal neurons. That is, there are neurons for which correlation can be as high as 0.6. And what is really interesting here is that the correlation for non-sarcastic neurons was higher than that for sarcastic neurons. And I think that makes sense to some level as well, because whenever we are sarcastic, the facial expressions don't really go or are aligned well with what we are saying, and that's the whole point. So the two modalities, which is your facial expressions and the utterances, they actually differ a lot. But in non-sarcastic content, these two things are much more aligned. That also shows up in the plot on the left. Finally, and the favorite slide and the favorite result of this paper, which is the marginal rate of substitution between modalities. So this is something that I hinted upon at the beginning of the presentation. And the idea was, if I want to get a particular performance on an image task, how many texts do I need versus how many images do I need? Can I come up with some conversion ratio that if I replace one image, how many texts do I need to actually replace that image and still retain the same performance? So this is what we are doing here, showing some heat plots, or where on the y-axis, left y-axis, we have the number of texts per class, and on the x-axis, we have the number of images per class. And the lines here show the heat map of accuracies, so like isoplots of accuracies. And you can fit a plane to this heat map, and you can find out that one image can be worth 1,000 words for this particular model, Dino V2 on the left. And on the right, we have an aligned model, which is CLIP. For aligned models, because they already know how images and text relate to each other, your conversion ratio is much smaller. So an image is worth 228 words in this case. So that's all about the project. Now coming to the key takeaways and discussion. So in this slide deck, we saw that multimodal data, even when fully unpaired, can be quite powerful, even on your domain of interest, even when it differs from the unpaired data. And you don't have to do anything fancy. All you need to do is share weights across different modalities, and the model should be capable to extract synergies between those modalities at some given scale. And that's the whole motivation and the pitch deck as well, which is don't treat data from different modalities as differently. That's all the data that represents the ground truth world. After processing them independently, they should all be treated as equal and passed through the same model to extract most of the information about the world. And some of the future directions that we are currently exploring is how can we leverage this unpaired data along with paired data. So there are some examples in the paper already which show that if you take a model like CLIP, which already has some pairing in the pre-training, you can still leverage unpaired data on top of it. And this is one plot, one table from the paper, which shows that as you increase data from different modalities, even when unpaired, you can have a monotonic increase in the performance. And this whole idea is very related and being pushed forward by some collaborators at Meta as well towards this whole idea of vision world models, where to improve vision, that is, have capabilities such as understanding about what's going on in the image, or predicting the next frames of a video, and so on. Don't just use image data, use all sorts of data present on the web, scrape all the data, put it jointly through the network, don't do anything fancy, and just a big enough model should be able to extract it. Some interesting questions to explore is what are the shared representations that these models are exploiting across the models? And this can be very powerful, especially in the domains where paired data is scarce, for instance, in robotics and healthcare. One thing that's missing and is of deep interest to me is, so far we saw that you can improve on image and audio or video using other modalities, but there's no paper in the whole field that shows that you can actually improve on text using other modalities. That is, can you improve on text using vision, video, and so on? So I think it'll be really interesting if someone can show something like that. Yeah, that's all. This is the project page. It looks like this, just to like get a sense of what the work is about and just a high level overview of the work. And if there are any questions, I can take them up now.